So guys, what we have here is a diagram shows a wedge of mass 8 kilograms. All of the faces are smooth, resting on a smooth horizontal table. One of the faces makes an angle A with the table, where tan A equals 3/4. The other free face is vertical. At the top of the wedge attached is a smooth light pulley. A light inextensible string passes over this pulley, connecting the particles of mass 5 kilograms and 1 kilogram as shown. With the 1 kilogram mass keyword here against the vertical face of the wedge. Okay? So, when the system is released from rest, the 5 kilogram mass moves down the inclined face with acceleration F relative to the wedge. The wedge moves to the right at an acceleration A. Write down 5 equations of motion answering the following descriptions. Okay, so here's what we're going to do. We're going to draw them out separately starting off. So start off with the 5 kilogram mass. Nothing we haven't done before. Does it tell me what it tells me there. Tan A equals 3/5. Cos A, guys, opposite over adjacent, so 4/5. And then sin A, 3/5. Okay, good start. Now, let's go directly down and directly across. Directly down, resolve F. Now there's no friction, is there? Does it say smooth? It says smooth, okay. We'll call this R. And then, so is there anything opposing the motion this time? Yeah, T. So T is going to be opposing the motion this time. So we actually have an extra letter added into our usual equation. Now, our 5 mg going directly downwards, and this one's going to be 5 mg cos A, 5 mg sin A. Just multiply it by 4/5 and 3/5 respectively, and what you're going to get is cos is 4/5, so that's going to be 4 mg when you multiply it out. And then sin A is 3/5, so if you're just to change that with 3/5, you'll get a 3 mg. Okay, we're good. Now, 5 kilogram mass along the inclined face. That's what we're working on first. So, any ideas? F. Oh, what do I have to do? Acceleration triangle. So we haven't done the acceleration triangle yet, because remember it's affected by the acceleration of the wedge. So there you go there. Acceleration triangle about to be created. There you go. Such an easy way of doing it. A, capital A. Now, A cos A sin A. So 4/5 A and 3/5 A. Okay, 4/5 A, 3/5 A. Everybody cool with that? Okay. So, 4/5 A, 3/5 A. Now, what we're going to do next is we need to do the formula here. So, F equals ma. The first equation wants us to go along the face, like so. So, what's our first answer going to be then? What's driving it down? Down the slope. What force is driving it down the slope? Now the answer can't be here because these are all accelerations. The answer has to be in the diagram above, where the forces are. These are all forces with the exception of F. F is just the acceleration. Everything else is a force. In this triangle here, everything is an acceleration, therefore it can't be considered a force. Okay, so therefore what we're looking at here is we're looking at you said 3 mg, was it? Now our tension working against our minus T, and that's going to equal what, guys? What's our mass? 5m, and then in our brackets, oh sorry, it's 5 kg, so this is just 5, not 5m. And then 5 times what? Now F going down, what's working against the F? So the F going directly down, but what's working against the F is your acceleration caused by your wedge. It's our minus 4 over 5a.
Shouldn't it be 3g mass T instead of 3mg since LCM?
So what did you ask me?
If you're only using m, shouldn't it be just 3g instead of...
It should be just 3g, shouldn't it? Ah, sorry guys, see my m's? Yeah, you're correct. Just came so accustomed to having m in it that sound off. Yep, you're right. Well done. So 3g minus t, then 5 into that. So multiply both sides by 5. Oh wait, no need to even. 3g minus t equals 5f minus, just minus, that's an a there, isn't it? So minus 4a. No, see 5 multiplied by 4 over 5.
3g in that is where it would have been 3mg.
Huh?
It's 3mg, so it's 3 but mass thing.
Just a note there, 3g basically means 3 kilograms multiplied by the force of gravity, hence it's a weight. It's a weight, okay? So, that there just so happens to be our very first equation. Okay? Done with one of them. Tick. Now we're on the next one. Perpendicular this time. So perpendicular is going directly downwards. Remember your R value. It's written in there already, thank God. So we're going directly down equals MA. So what forces are going directly down and directly up? Directly down. 4G directly down, opposing the 4G. The R value going directly up. So 4G minus R. What's the mass of the object? What'd you say? 5. What's the acceleration going in that direction? 3 over 5a. Good man. And then once we do that, 4g minus r equals 3a. Second equation, done. Now, we've done, pretty much exhausted our information there, so what we need to do next is we can just box this off here. All this information we just worked out is not going to be used anytime soon. Box it off and box that off down there as well, the acceleration triangle. Okay, so what we're going to do next is we're going to be working exclusively on the pulley, or the part that's hanging. Okay, so we're going to start working on the 1 kilogram mass along the vertical. So this 1 kilogram mass is currently hanging. Okay, so it's very easy. 1 kg, 1 g directly down. What brings it directly up? Anybody? T. What way is it going? Up or down, acceleration wise? It's going directly up at F. Is it affected by A at all? They're at 90 degrees to each other. If they're at 90 degrees to each other, they're not affecting each other. The only reason A affects F is because F and A are not at 90 degrees to each other. If the wedge's acceleration is 90 degrees to another acceleration, they have no effect on each other in that direction. So we are considered, because this is going directly up, we're going to work directly up and directly down, hence the word along the vertical. Okay, so let's start off. F equals ma. Force is going up cause an acceleration to go up. What force is going up? T. What force is going down? 1g, or otherwise known as g. Mass 1, acceleration F. So here it is. F equals T minus G. Part 3 complete. Okay? Now we're on part 4 along the horizontal. Now, when it comes to the horizontal, what's happening to this diagram when it comes to the horizontal? It's in contact, isn't it? It's in contact. So we'll call this, or the wedge is experiencing contact on its way in, but it's also pushing it along. See, it's hanging in front of the motion, so it has to be in contact. Because if it's hanging freely and then this object keeps moving into it, they're going to be constantly in contact. Okay, so what can we say about, there's a force acting on it and there's a reaction force pushing it to the right. Okay, we'll call it R1 because I've already used R earlier on. Okay, so F equals ma, and we're going directly across this time. So anybody want to tell me the answers for this one? R equals mass 1, acceleration in that direction A. R equals 1A. It's that easy. Okay, group that one, and then that one is getting sent down here as well. Now, next one, the wedge. Here's the hard one. Now, the wedge, okay? So we're going to draw our wedge like we always do. Okay, so the wedge is drawn. Now, let's do what we always do. The wedge's acceleration goes in which direction? Sorry? So it's going to the right. The wedge along the horizontal. So we have to figure out all the wedge's forces along the horizontal. So, we got to resolve R, not R1 but R. R goes in this direction. What angle is this again? A. So makes that R cos A and R sin A. Does anyone remember what cos A and sin A are? What's there? So it's 4 over 5R and 3 over 5R. 4 over 5R and 3 over 5R. Everybody right with that? Now, anything else opposing its motion? Yeah, I didn't use S though. Oh, I used R1 coming in from this side here. You might have been talking about the supporting reaction force underneath, but because that's going directly vertical, it doesn't influence left or right. Okay? So lads, we have to make our wedge formula now. Now, we've left one thing out here. Anybody tell me we've left one major part out? We haven't mentioned tension at all. For every force, there's an equal but opposite reaction. So, we forgot all about our pulley up here. And our pulley is causing tension to occur. So we have tension and, sorry, I'll just do this properly here. Tension going down this way, tension going that way. Okay? So what we might do here is we might try and see what's going on here. So if you have a weight, if you have a big weight down here, what way is that pulling you? Imagine you're the person pulling it up. What way does it affect you? It's going to force you down and to the left. Would everybody agree with that? If you're pulling somebody up a hill or pulling an object up a hill, that object wants to pull you down the hill and back down the direction of the hill. So there's two forces at play here, two components. So we can say that this here is an alternate angle to A. Everybody agree with that? Alternate angle. It's called T. T is the hypotenuse. So what does that make that? T cos A and T sin A. T cos A, T sin A. Everybody agreed? Now, T cos A, T sin A, otherwise known as 3 over 5T and 4 over 5T. Good? Now, F equals MA. A going to the right, F must also sum up to go to the right. So what's driving to the right? And with 3 over 5 R minus R1 minus 4 over 5T equals, anybody? Equals, what's the weight of the wedge? 8. 8A. Now, so it states that the two tension forces will act as external forces on the wedge, also like the lasso around the neck. This is their explanation. I'm going to do one last equation just to show that it can be done. Don't rarely ask it anymore. But do you know why there's one that's going left and, do you know why that's the wedge going left and right? You can also do a wedge going up and down. So I'll show you what I mean now. Get out there, get out there, get out there. So what we can do is, it's called statics. Why do you think it's called statics? Is the wedge either moving up or moving down? So it's called statics because the forces up equal the forces down. They have to balance each other out. Or, other way of doing it is forces up minus forces down equals 0. Where MA equals 0. Because there's no acceleration up or down, is there? Because the wedge isn't leaving the ground, nor is it sinking into the ground. It's staying where it is. In the same way, my bag is not accelerating up and down at the moment. It just is where it is. Okay? So let's try this one out. What forces go, and we also got to take into consideration, what force here? 8 mg. I'm going to take the weight of the wedge into consideration. Is that alright? Now, what forces are going down, or up I mean, forces up? S. Anything else going up? Absolutely nothing. The only thing keeping that wedge up is the ground. Okay? What goes down? 8. Oh, sorry, it's 8G, not 8 mg. Did the same thing again. It's just 8 kilograms. 8G. After that, 3 over 5. Oh, sorry, 4 over 5 R going directly down. Yeah. Anything else? Minus 3 over 5 T, and all that will equal 0. So you can see there's an extra equation if you ever thought you needed one, but for the most part I think there's like a 1 in 1,000 chance you're going to use that in your leaving cert. It can happen, but we'll see. Just be aware of it.